you can start with the introduction whenever you
Sure.
like.
Okay. Um, Welcome to another of our quantum matter seminars. Today we have the pleasure of having Frank Kruger, who is a professor at the University College London with a shared appointment at the Neutron Scattering Facility in the UK. Actually, before being at UCL, Frank was a lecturer in St. Andrews, where I started my PhD. So we know each other for many, many years now. And it's my pleasure to host him today on his talk, Nature of Topological Phase Transitions of Kitaev Quantum Spin Liquids. Go ahead, Frank, floor is yours.
Okay, yeah, thanks a lot for the invitation and the introduction. So, yeah, please interrupt me while I go along. This is quite new work, which is still under review, and yeah, I appreciate questions and feedback. So, yeah, I'm going to talk about the nature of the topological phase transition in Kitaev quantum spin liquids away from the exactly solvable point, which in reality is always the case because you never have the idealized Kitaev model. And of course, as you might know, you can have a topological phase transition from a gapless quantum spin liquid to a gapped quantum spin liquid. And the question is whether this is a trivial transition or an interesting transition that shares some of the features that electronic phase transitions in strongly correlated Dirac semi-metals have. Okay, so let me, oh, I'm already stuck. Oh, no, okay. So let me first introduce the people. These are all people from my group. So Suresh was a master student, and a bit of the mean field theory that I'm going to briefly talk about was done by him in his master project with the help of one of my PhD students. Then the main part of this talk will be about a very recent paper where we use a field theoretical approach to understand the nature of the phase transition, where we not just motivate the form of the field theory, but we are explicitly going to derive it starting from the lattice model. So, of course, you all heard these general introductions about quantum spin liquids. So the negative characteristic is that you have no long-range magnetic ordering down to absolute zero temperature. And this is, in most cases, due to geometric frustration. So one of the main ingredients is to have a frustrated lattice like the triangular lattice or the Kagome lattice in 2D or the pyroclo lattice in 3 dimensions. Right, but the absence of order is a negative characteristic, and of course you want to say something positive, and of course one feature is that you have non-trivial topology of the ground state wave function. Then you have long-range quantum entanglement between your spin degrees of freedom, so you could think of some type of RVB state as discussed by Anderson a long time ago, right, where you have this kind of dimer covering of the lattice, but the wave function is a superposition of all kinds of coverings, and here it's drawn for nearest neighbor dimer covering, but you can also imagine that you have longer range singlets over more than nearest neighbors. Right, and once you have this, you can think of a magnetic excitation, which would be a spin 1 excitation here. And this can usually deconfine and fractionalize. So the magnetic excitation, spin 1 excitation, breaks up in two spin-ons, which could move around like new emergent degrees of freedom. And depending on what type of quantum spin liquid you have, you can have very different features and different emergent particles, spin-ons, Majorana, fermions, non-abelian anyons, and so on. Right, so this is all kind of very unspecific, but in general, once you have fractionalization, it always comes with some gauge degrees of freedom and some gauge structure. And experimentally, what fractionalization means is that you can divide up energy and momentum in infinitely many ways. So rather than having sharp quasi-particle excitation in inelastic neutron scattering experiments, you will see a continuum in energy momentum, right? And this is, of course, known for the deconfined spinons and the spinon continua in one-dimensional spin 1/2 chains, and understood with beta ansatz and so on. But it's much harder to understand in higher dimensions, in two-dimensional quantum spin liquids. So I just show one very recent paper that is, I think, still under review. So the theory was done by Joel Moore using DMRG, and then the neutron scattering experiments were led by Sarah Harifafard. So above you see the measured inelastic neutron scattering spectrum, and you really see these continua. And they say that this is evidence for the presence of a quantum spin liquid state. And the system has these sheets, which are triangular lattice antiferromagnets. So, of course, if you just take a Heisenberg antiferromagnet on the triangular lattice, you know that you get an ordered ground state, the so-called 120-degree state. But if you switch on a small J2, if I remember, it's something like 0.06, numerics predicts that you enter a quantum spin liquid state. And they claim that their materials are in this ballpark regime. Of course, there are other complications. You always have disorder, especially if you look at a complicated compound like this. There is also exchange anisotropy and so on. But the agreement with DMRG looks quite convincing, I would say. Of course, to really see, you should not look at these color maps, but maybe show the scaled intensities and compare the two. But if it's not a quantum spin liquid, it's very close. And you see the excitation continuum. So, of course, DMRG doesn't tell you, so you basically start with the spin Hamiltonian and everything comes out by magic. It's a bit of a black box. So you don't really know what the emergent particles are and so on. Right? So that's why the Kitaev model is really a blessing, because it's an exactly solvable model that has a quantum spin liquid ground state. And you see it's defined on the honeycomb lattice. It's not a geometrically frustrated lattice. So the frustration here really comes through the exchange couplings. So you have three bonds, and on one of the bonds, you only have an SZ-SZ coupling. On one bond, only SX is X. On the other, only SY is Y. So it's like a bond directional Ising exchange. So Kitaev didn't really care if such a model is feasible. Of course, theorists can write down whatever they like. And these sigmas are just the spin operators in units of h⁻², satisfying the standard commutation relations. So this is the Kitaev model. And what Kitaev showed is that you can exactly solve it if you rewrite your spins in terms of pairs of Majorana fermions. So these are fermions that if you dagger them, you get the operator itself. So you need 4 of these Majorana fermions in his representation. They satisfy the standard Clifford algebra. So if you look at this, you immediately see that if you take one of the etas and square it, you get 1, which will become important later. And in order for these to really reproduce the spin commutation algebra, you need an additional constraint to really match the Hilbert spaces of the Majorana fermions and the original spin 1/2 operators. So this is the kind of graphical representation of this. So on every side, you have this set of 4 Majorana fermions. But then the model is such that on the X bond, you have the eta X involved. On the Y bonds, the eta Y, and so on. And if you rewrite your Hamiltonian, it looks like, at first glance, you don't really gain anything because it's now a quartic Hamiltonian. So it's not quadratic, so it's not a non-interacting Hamiltonian. So what can you do with this? So first you see, as I said, that only the eta naught is defined on every lattice side, right? And then the other operators just live on particular bonds which are disconnected from one another. And if you look at these bond operators, I eta gamma, eta I gamma, eta j gamma, for gamma is x, y, z, and you square it, you get 1. So these bond operators have eigenvalues plus minus 1. And what you can now define is a plaquette operator by just taking the bond operator, the y bond operator times the x bond operator, and so on around the plaquette. And this also has eigenvalues plus minus 1. The nice thing is that these plaquette operators commute with the Hamiltonian. And also, if you take plaquette operators from different plaquettes, they also commute. Which means you can simultaneously diagonalize the Hamiltonian and all these plaquette operators. Right, so you can look at the configuration of these, and what you define are fluxes. So if you have an odd number of excited bonds around the plaquette, you say you have a flux on this plaquette. Right, so for each flux configuration, you can then diagonalize your Hamiltonian. But if you have a certain flux configuration, it turns into a non-interacting problem. So the question is, what is the ground state? And it's also important to say the only thing that is physical here are the fluxes, not the realization of the bond variables that give rise to this flux configuration. So you can, for example, have here 0 flux with 2 excited bonds or no excited bond, right? And states with the same flux configuration are linked by gauge transformations. So the ground state, and in Kitaev's original paper, he basically used numerics to show that the ground state is the 0 flux state. But there is a theorem called the lead theorem that tells you that if you have a plaquette that has 2 modulo 4 bonds around, so 6, for example, in the ground state, you have 0 fluxes. So one realization for the bonds giving 0 flux is if we have no excited bonds, if we replace these bond operators all by plus 1. Right, and what you then get is a 2 by 2 Hamiltonian for this eta naught fermion in this sublattice space. And this complex function gamma naught is just given by kx plus kz plus kx e to the I ka1 plus ky e to the I ka2, where a1 and a2 are just the unit vectors of your unit cell. Right, and the dispersion you get is just given by plus minus the absolute value of this function gamma naught. And if you look at the isotropic case, what you get is exactly the same as the tight binding dispersion of graphene. Right, so you have Dirac points at the edges of your Brillouin zone. Okay, so but of course this exact solution also allows you to look at anisotropies in the Kitaev couplings. And this is also looked at in Kitaev's paper. So let's, for example, consider the case where we make the kz larger than kx and ky, which we keep the same. So what happens in this case is that the Dirac points move along the edge of the Brillouin zone. So the Dirac points move like this, and these points move like this. So you still have 2 Dirac points in your unit cell. But at some point, these will merge. And when this happens, you have a topological phase transition. So what I've shown here is this gapless band, which is the eta naught band. And I've shown one of the gapped ones from the eta z fermion. And since these just live on a bond and have no dynamics for the pure Kitaev model, the band is completely flat. So here you see, if you make kz larger, the Dirac points move towards one another, like shown in this cartoon here, and then they touch when kz is exactly twice of the other two Kitaev couplings. Right, and what you get is a so-called semi-Dirac point. So it's a quadratic band touching in the merging direction, and it's linear relativistic in the perpendicular direction. And this has been called semi-Dirac point. And then if you make the kz even larger, you open a gap. And this gap state, if the anisotropy is large, can be mapped to the Topological model, which is the poster child for quantum error correction and so on. And a lot of Kitaev's paper was actually on the link to the Topological model. So you see, the transition doesn't look special here, right? It just looks like tuning of a tight binding dispersion. It looks like a non-interacting problem. So the question is, what happens if we move away from this exactly solvable model? So, of course, the whole field took off when Kitaev's model was connected to reality, right? And this was done due to the work by Jakeli and Kaluyin, who basically argued that if you have systems with strong spin-orbit coupling, strong spin-orbital entanglement, you can get this bond-directional Ising exchange, right? So they look at these A2BO3 layered compounds where you have these planes, hexagonal lattice planes, right? And on these A sides, you want to have magnetic ions with partially filled T2G orbitals and strong spin-orbit coupling, like elements like ruthenium or iridium. And indeed, there were a lot of systems from this class, lithium iridates, right? Several variants with slightly different lattice structures. And then there is also this Kitaev candidate material, alpha ruthenium chloride. So in all these, you are close to the Kitaev model, but of course, the bond angles are not perfect. So you always get additional Heisenberg couplings. You can't avoid second neighbor interactions and so on. So it's not a pure Kitaev model, and many of these actually show long-range magnetic ordering at very low temperatures, but this is very fragile, can be destroyed by small fields and so on. But yeah, I think it's only a question of time to get a material that really has a quantum spin liquid Kitaev ground state. I mean, it's debated if some of these already tick the box, but I'm not going to answer this question. Also, what I want is some additional stuff to get away from the exactly solvable point. So, of course, what you get as additional couplings depends on the particular realization. But the point is, if you switch on anything here, the model is no longer exactly solvable. So these bond operators no longer commute with your Hamiltonian. So all this construction doesn't really work. Right, so what we would expect is that the topological phase transition is no longer trivial. And at some point, we also expect that there will be magnetic instabilities, and what type of magnetic long-range order we stabilize will crucially depend on the additional couplings we have here. Okay, so we expect interesting phase transitions, and the reason why we got interested in this problem is that we've worked on quantum criticality of Dirac systems and semi-Dirac systems, and we thought we should explore similarities between electronic phase transitions and the quantum phase transitions in quantum spin liquids, in particular Kitaev quantum spin liquids. So let me just flash up a few slides on the situation in electronic systems. Of course, you can get Dirac electrons in low energy theories of Connes matter materials, right? So they appear in Connes matter settings, but as we will see, you can also have exotic things like semi-Dirac points, which you won't get in high energy physics. right? So you can make the situation much richer. So we take, let's say, a tight binding model on the honeycomb lattice. Of course, because of the vanishing density of states, you don't have a weak coupling instability. So you need strong interactions to get a broken symmetry state, right? So you could take on-site Hubbard repulsion, which gives you an antiferromagnetic state, or you can take a nearest neighbor repulsion, which gives you a charge-ordered state, right? So these don't enlarge the unit cell because you already have two sides in your unit cell, but they break the symmetry between the A and B sides. And of course, here you also break the spin rotation symmetry. So this would be described by an Ising order parameter, this by an O3 order parameter. So a lot of the theoretical work early on was driven by Igor Herbut, who really made this connection between the condensed matter situation and the Gross-Neveu-Yukawa theory, which has been known to the high energy guys for a very long time. So the effective field theory you study is basically your standard Ginzburg-Landau phi to the 4 theory. But this is then coupled to Dirac fermions, right? And the coupling is just the standard Yukawa coupling, where you have your order parameter coupled to this bilinear of the fermions, and it's coupling through the sigma z Pauli matrix in sublattice space. So what it means, if the order parameter condenses, this will be finite, and then you basically have a potential between A and B sides, and you break the symmetry and open a gap, right? It's like putting graphene on boron nitrate, so you would open a gap. But here, the gap opening goes hand in hand with the spontaneous symmetry breaking of some order parameter. So the RG flow in 4 minus epsilon space-time dimension just below the upper critical dimension is sketched here. So what the important thing is that the Wilson-Fisher fixed point becomes unstable towards this coupling to fermions, and you get this, what people call this fermion-induced fixed point. And another important thing is, because you have this order parameter theory coupled to gapless Dirac electrons, you are not allowed to just naively integrate out your gapless fermion modes, right? The general rule is you can only integrate out gapped modes. So this is like a baby version of the real fermionic quantum criticality problem, where you can do control calculations because of the fact that you just have point-like Fermi surfaces. But some features are the same to the real problem. So at this transition point, your quasiparticle residue vanishes, right? And you have an electronic gap opening in the broken symmetry phase. And the fermions acquire some anomalous dimension, which means that you no longer have quasiparticle poles, but branch cuts. So you get non-Fermi liquid behavior. So you can treat this in 4 minus epsilon, or you can stay in the physical dimension, 2 space dimensions, and generalize to a large number of fermion flavors and to some large n. And interestingly, the RG results of the field theory agree remarkably well with quantum Monte Carlo of the 2D lattice model, and also with conformal bootstrap methods. And but also for the epsilon expansion, I think people have now calculated up to 4 loop order and so on. So so that's all very well understood. And of course, you can also get a topological phase transition in the electronic systems, right? So you can take a tight binding model and just make one hopping along the Z bond different, and you get exactly the same thing, that your Dirac points get closer and merge, and then you open a gap, right? And it's T prime over T is 2, same as KZ over K is 2. So really the dispersions of the Majorana fermions in the tight binding dispersion identical, right? And this is just sketched here. And the effective long wavelength Hamiltonian just looks like kx squared plus delta, and then you have ky sigma y. So quadratic linear. If delta is 0, you are exactly at the semi-Dirac point. If delta is positive, you have a gap. If delta is negative, you have two solutions. Kx is plus minus square root of minus delta, and you have the two split Dirac points. Okay, so we will recover this. And of course, in the electronic system, you can image the electronic band structure using ARPAS, right? And there is a system that is well described by this anisotropic tight binding model, and that's black phosphorus. It has some honeycomb layers which are buckled, so you have this one very strong coupling. And what they managed to do is tune this gap by sprinkling potassium onto the surface, which gives you surface doping and Stark effect, and you can tune the band structure. So here you see how you can tune the gap down to 0. In a later paper, they also managed to go to the other side of the transition where you have the two Dirac points. Unfortunately, we can't do ARPAS on the quantum spin liquid systems, right? We can only do inelastic neutron scattering. And what has also been done is looking at the state where you have semi-Dirac, so you tune delta to 0, then you look at interaction-driven symmetry-breaking phase transitions. And because you now have a semi-Dirac point, the universality of this transition is different, right? So you start now with a free fermion Hamiltonian, which has this semi-Dirac form. You have your Yukawa coupling. You can consider charge density, spin density, order parameters, superconductivity. And this has been studied a lot, including by my group, but also Chubukov and Roy and Foster and so on, using various different techniques, epsilon expansions, large N, and so on. So, but let's go now back to the Kitaev model and see if we can get something similar. So the question is what to add to have a model that is not exactly solvable, but where we can still to avoid some of the complications like this constraint in the original Kitaev construction. So what we actually add here on all the nearest neighbor bonds is an Ising coupling. Just spin Z. So it's not exactly solvable. And the J, if sufficiently large, will stabilize in Ising antiferromagnetic state. Okay, but we are mostly interested in the topological phase transition. And actually what we will see there is quite generic and doesn't depend so much on what we will add here. So we also looked at more realistic models beyond the Kitaev model. So we have an anisotropy parameter, which is just from making kz larger than k, and then we have the dimensionless ratio of j over k. The reason why we used this, and other people did as well, is you can use a two-dimensional Jordan-Wigner transformation, which is an alternative way to get the exact solution of the pure Kitaev model. So probably you all have seen the Jordan-Wigner transformation in one dimension. So of course, what you can do is you can represent the spin Z by 1 minus 2 C dagger C, where C and C dagger are just spinless fermions. So the Hilbert space is just no fermion or one fermion. And you see immediately this reproduces plus minus 1 for the spin operator. And of course, the zero and no fermions, the zero and no fermion states, if you identify them with spin up and spin down, the sigma plus, sigma minus need to be identified with C and C dagger. The problem is the fermion operators anti-commute on different sides. The spin operators commute. So you need to repair this discrepancy in the commutation, anti-commutation relations. And this can be done by introducing this semi-infinite string operator. So basically for the side n along the string, you have a product over all the sides to the left of this side. So of course there is some redundancy how you put a one-dimensional string in a two-dimensional lattice to cover all the lattice sides. For this particular model, what we want to do, you see the X and Y bonds are nearest neighbor in the two-dimensional lattice, and they're also nearest neighbor in the string. And if you multiply string operators from neighboring sides, almost everything cancels out and the Hamiltonian stays local. The problem are the Z bonds. They are nearest neighbors on the honeycomb, but not nearest neighbors along the string. So you would be left over with segments of string operators, resulting in a non-local Hamiltonian, unless all the couplings along the Z bond only involve spin Z components, which is true for the pure Kitaev model, but also true if we add an Ising coupling on all the three bonds. So that's just an idea that has been used before, and we only get two Majorana fermions, so you can easily relate the spinless fermions to Majorana operators, right? If you take C dagger plus C, it's a Majorana. If you take C dagger minus C multiply with I, it's another Majorana, right? And your Hamiltonian looks like this. So for the Kx and Ky bonds, it's already quadratic. That's an advantage over the Kitaev construction. And then you get a quartic term from the Kz coupling. And these etas, again, are just living on these Z bonds here. Right, so again, you have these bond operators which give rise to plaquette operators, and you get the same logic I presented before. But then, of course, if you have this additional J, you get additional interaction terms. So this is no longer exactly solvable in the presence of this J, right? But to get a feeling of how the phase diagram looks like, we can now just do a mean field treatment, introduce these expectation values of these bond operators for the gapless ones and for the gapped ones. So for the pure Kitaev, this would just be plus minus 1, right? But now we have fluctuations dynamics. So this can now take some general value. So we introduce these on all three nearest neighbor bonds, and then the staggered magnetization. And then you solve it self-consistently, and this is the phase diagram you get. So this is anisotropy of the Kitaev couplings. So the mean field treatment reproduces the transition point Kz is 2K of the topological phase transition. And in fact, mean field theory will become exact for the exactly solvable case. And this will also become clear from our field theory treatment. So as expected, if you make the J large enough, you get an antiferromagnetically ordered state. We find that this transition is first order. It's not an artifact of this particular choice of interaction. It seems to be very generic. It's found everywhere. So we first thought we look at the magnetic phase transition, but yeah, it's first order, so there is no universal critical behavior here to be investigated. But of course, you still have the topological phase transition. And if you look at the mean field dispersion across this, so you see that the gapless mode basically does the same thing as for the exactly solvable model. But now the gapped one becomes dispersive, right? So these are no longer local degrees of freedom. They are now dynamical because of the J that gives them dynamics. Okay, so this is the problem we want to study, okay? The nature of this transition. So, of course, in order to study this, we want to derive an effective field theory. We don't want to use hand waving to write down the form we expect this field theory to have, but we want to derive it systematically. So we start with our lattice model, right, where we now have the gapless mode and the gap mode. So these complex functions, psi and lambda, are again these sums over these exponentials for the three bonds. So the mean field dispersion is just linked to these functions, plus minus the absolute value, right? But it's important that this one is gapped. So the BZ will be larger than twice the BX, BY. Right, so this is gapped, but has momentum dependence. Right, and this is what we found in our mean field theory. So the precise value of these parameters A and B is not really important for this, but by symmetry, AX will be the same as AY and BX will be the same as BY, but the values for the Z parameter will be different. And the same is true for the interactions, right? So we have interactions GX, GY, GZ, which are of this form. So this is just what we got. And for the pure Kitaev, we only have the GZ, right? But once we have J, there is also GX and a GY. And the interaction couples the gapless one. So it's across the bond, right? It's phi A R and then phi B R plus delta gamma, where we have gamma as X, Y, Z corresponding to the three bonds. And then we have this bond operator for the gap mode, right? Again, for the pure Kitaev, you just replace this by +1, right? But this is no longer allowed. These are now fluctuating degrees of freedom. So here we can indeed integrate out the gapped mode. And if you integrate out the gapped mode, you will derive an effective interaction for the gapless Majorana fermion, right? Just shown in this diagram here. And you can actually do this exactly up to the point where you just have here momentum frequency integral, right? But because this is a gap mode, there is no divergence, so this will be some convergent integral. Okay, and all this we just dump into some interaction strength parameter. So what these interactions actually mean, we now have interactions between bond operators for these gapless Majorana fermions, right? And what it means is it's an interaction between a bond operator, let's say, along alpha, a bond operator along beta, coupled through a bond along gamma. This is what this rho alpha beta gamma means. So for example, what I've pictured here would be rho ZZ X or rho ZZ Y, right? It's a bond operator Z, coupled either through a Y bond or through an X bond. So the reason why the interactions look like this in real space is because if you take a Majorana on the same side and square it, it's 1. So it's no longer an interaction, right? So all the leftover interactions will actually involve Majoranas on 4 different sides. So far, so good. So now how can we recover here that there is an exactly solvable point? So let's take the case J is equal 0. What happens for J is equal 0? As I said, the GX, GY interactions are 0. And the gap mode becomes dispersionless, which means BX, BY is 0. So this implies that all these rho alpha beta gammas are identical to 0, which means for the pure Kitaev model, all these interactions disappear. and we just get a free fermion theory. So how to see this easily? So yeah, if you look at the row alpha beta, it involves G alpha G beta. So this means only the interaction between the bond Z operators can be non-zero, so only these two, right? But then for the link gamma, it involves the B gamma, but the coupling is either through an X or Y bond, and the BX BY is zero. So all the rows are indeed zero. Okay, but in our situation now, we have all these rows. And what you now want to do is you want to get the Gross-Neveu-Yukawa coupling. You want to do a Hubbard-Stratonovich decoupling of these interactions and introduce some dynamical order parameter. And then you want to do a coarse graining, expand around the semi-Dirac point. So what we actually just need is the linear coupling, the form of the Yukawa coupling, for reasons that will become clear later. And the form can also be obtained from mean field decoupling. So again, you can introduce bond expectation values. And what you then get after this mean field decoupling is this linear coupling, where this omega gamma is a linear combination of these, right? Because for a given bond, expectation values of various bonds that couple to it through different rows will enter, right? So the row Z, for example, is given here. It's a linear combination of phi X, phi Y, phi Z. So you now perform a Fourier transform, and then we want to zoom in into the topological phase transition where we have gapless excitations at this semi-Dirac point. So we want to expand around this point. And if you do that, you get exactly this kind of Yukawa coupling where this Ising order parameter field, this dynamical fluctuation field, is just some linear combination of these omegas. Right, so you see immediately the coupling is just off diagonal in this 2x2 sublattice space, right? So it can only enter through Pauli matrix sigma X, sigma Y. And here, since we have this additional I, it will enter through sigma Y. So this looks like in the electronic problem, but here the coupling, the Yukawa coupling, is not through sigma Z, which would just open a mass gap, but it's through sigma Y. So of course you also want to take your tight binding like dispersion and do a continuum limit and expand around the semi-Dirac point. And of course you just get this long wavelengths semi-Dirac form with this effective tuning parameter delta. Right, so not surprisingly, this dynamical fluctuation field couples in exactly the same way as this static tuning parameter, right, along the quadratic direction. And we just rescaled the momenta and renamed them. So K0 is frequency, KL is the linear, and KQ the quadratic direction. So why do we not need the other forms, for example, the phi squared phi to the 4 term? These would be generated under RG anyway, right? So you can now take this Yukawa coupling and look at these diagrams. So they will be generated under RG. So you just need to include these terms in your free energy theory anyway. So the phi squared, of course, would also be there from the Hubbard-Stratonovich decoupling. Okay, so far so good. So one very crucial point is we want to work in 2+1 dimensions, so 2 space dimensions. And there is a crucial difference to the calculation in 2 space dimensions to the epsilon expansion. And that's because of the phenomenon known as Landau damping. So actually, this kind of self-energy if you calculate it not on shell in the RG, perturbative RG, but you calculate the self-energy by doing this bubble diagram over the full frequency and momentum range, actually in 2 dimensions, there is a non-analytic behavior. And this non-analytic term, the scaling of this, dominates the long wavelengths IR physics. Right? So it's the same as Landau damping, that the order parameter fluctuations get damped by electronic particle hole fluctuations. And this completely changes the universality of the transition. And the same is true for the emergent Majorana fermions. So this has actually been pointed out for the symmetry-breaking phase transitions of semi-Dirac fermions in this work by Chubukov, Shmalian, and Nagaosa. And what you actually should do is you should use an inverse Green's function, which is basically of the scaling form where you just take the IR of this self-energy correction. And then you use this as input for your perturbative RG calculations. And what we have demonstrated is that if you use the scaling form, we've used some soft cutoff scheme to prove this. If you use the scaling form, indeed the perturbative RG is completely universal in the sense that your results don't depend on what UV cutoff scheme you use in your perturbative RG. So you can use whatever cutoff scheme, you just get the universal quantum corrections. So the problem is, this is not so easy to calculate if you have no simple Dirac fermions, but the semi-Dirac spectrum. You can't calculate this integral analytically, but you can show that this self-energy is of the form mod QQ, and then some function which is given by the ratio of Q naught squared plus QL squared over QQ to the 4. And you can look at the asymptotic behaviors if either the linear directions are 0 or if the quadratic direction is 0. So you see this non-analytic form which dominates the conventional gradient terms you would get from just doing a perturbative shell integration. And this function f can actually be written in terms of a 2-dimensional integral, which you can calculate numerically. So we will, in the following, just use this numerically obtained form of this function f here. So, as I said, the UV cutoff scheme is not really important, so you can use whatever is convenient. And what's used for Dirac fermions, typically, but also for the semi-Dirac, is shells in frequency momentum space. So you go to 3-dimensional frequency momentum space, and you don't integrate frequency over the whole real axis, right? But the results are the same. So, the shells we have are just defined by epsilon squared as k naught squared plus kl squared. But then the crucial difference is that we get kq to the power 4, right? And we integrate over these infinitesimal shells. So actually, you can do the integration by using generalized spherical coordinates, right? Which look like spherical coordinates with the difference that the z, the kq, enters here as a square. And the integration range is slightly different to cover the whole range. And you get some quite ugly Jacobian from this transformation. Okay, but yeah, you can do the integration and you do the rescaling in the same way. So if you plug in the transformation of this argument here, you get tangent squared of the theta angle. And this is what we previously called U. Right, so then the diagrams you calculate are the self-energy diagram that renormalizes the fermion propagator, right? And you can calculate it, and what you get by after expanding out the outer momenta to linear and quadratic orders, you get something which is exactly of the same form as the original propagator. So basically, this renormalizes frequency and the velocity of the linear term, and then you have a different renormalization of the quadratic term. Because these shell integrals are different, you have to adjust your scaling exponent for the quadratic momentum direction to compensate for this difference. Right, and everything can be written in terms of a last one-dimensional integral over theta, or this variable u. And this function f is also determined numerically, so we can calculate the numerical values of this. Right, and as I said before, we just generalize to n copies of our semi-Dirac fermions. So what can we actually read off from that? So the scaling of the quadratic momentum direction with respect to the linear would just be a half a tree-level scaling, and then we need to compensate for the difference in the renormalization. Right, and so this ensures that that basically we just have an overall renormalization, and then we just adjust the scaling dimension of your fermion fields such that the whole free fermion propagator remains scale invariant. Right, so this gives you your scaling exponent ZQ and your anomalous dimension for your fermion, Majorana fermion field. So then you can look at the renormalization of this delta, which is a relevant perturbation. And this, so you always flow away, and the coefficient just determines what you would call correlation length exponent. Right, so 1 actually is the mean field exponent you would get without interactions. It looks different to the conventional because we have Dirac fermions where what used to be a half is 1 for Dirac fermions. So we have this set of exponents, and then we can look at the renormalization of the Yukawa coupling. So this gives you a correction to the Yukawa matrix, but it's again proportional to sigma y, which means the only thing we renormalize is the coupling constant G. Right, and this shell integral by accident is equal to one of the shell integrals we have already calculated. I don't think there's a fundamental physical reason for why these integrals are the same. So we get the RG equation for the Yukawa coupling strength, just the rescaling and then the quantum correction from the diagram. But then there is an important point. So you see the Yukawa coupling is linear in this fluctuation field, the bosonic fluctuation field. And the propagator is phi squared, but it has a g squared in front. So actually you can completely scale out the g just by defining a new field as g times the old field. So you can completely scale out for this theory in 2+1 dimension the g, which means it is scale invariant. So we need to postulate that the G doesn't flow, which the only thing that is unknown here is the scaling dimension of your bosonic fluctuation field, which is also fixed. So now we can use this and look at what happens to the phi to the 4 term. And if you stick everything in, you find that it's actually irrelevant. It's no longer irrelevant if you go to 4 minus epsilon. There it's marginal as well. But in 2+1 dimension, it is irrelevant. But this is because of the unusual scaling that is set through this non-analytic IR propagator. But as I said, all these considerations are not new. They all have been addressed and carefully studied in the case of symmetry-breaking transitions in semi-Dirac electron systems. So what does it mean for experiments? I'm almost I'm almost done. So the question is, can we actually measure any of this, assuming that we have an experimental realization of a quantum spin liquid, and we can tune it through a topological phase transition? I mean, these are two steps that are far from obvious, right? Because if you apply strain, you would not only tune the Kitaev couplings, but of course you would also potentially increase other couplings you have and stabilize magnetic order, right? But I mean, black phosphorus came along where you are already very close to this situation, right? And it's where basically some atoms are moved out of the layer and so on. Maybe something clever like this can also be found for the Kitaev spin systems. But then, of course, you can't do ARPAs, right? So how could you actually see features of these experiments in inelastic neutron scattering? So, of course, the exponent nu delta is linked to how the Dirac points split on one side of the transition and how the gap in the electronics in the fermionic spectrum opens on the other side. Right, so the gap opens with the exponent nu delta, and since we have a square root of minus delta here, you get an exponent nu delta over 2 for the splitting on the other side. So, of course, the magnetic excitations, the intensity itself is hard to calculate, but if you want to have the boundaries of your continuum, basically you can read it off, and this exercise, of course, you might have done for the spin-on continuum in 1D chains, right? So the magnetic excitations correspond to particle-hole excitations. And of course, you can just look at the energy momentum transfer and get the boundaries of your continuum from that. So for example, here, you can get a particle-hole excitation of 0 energy and this finite momentum transfer. So you expect that the spin continuum goes to 0 at the wave vector that is given by the splitting of the Dirac points. That's one thing. So if you can measure the continuum across the topological phase transition, you can, in principle, extract this exponent if you have enough resolution. And of course, then also this gap, 2 delta, will be linked to the gap of the spin continuum. So that's one thing. And the other thing is this exponent eta phi, the anomalous dimension. I mean, theoretically, it tells you that, again, your quasi-particle description breaks down at the critical point, right? And you get Majorana non-Fermi liquid behavior, if you like. But what this will also do, I haven't looked at the precise form of the expressions, but what it will do, it will change the algebraic decay of spin-spin correlations, right? It will enter in the exponent and modify this. And this should also change features in the continuum. And then something that I think is not very well explored is what really you can learn from quantum Fisher information. So there is a lot of activity that quantum Fisher information is a witness of quantum entanglement, but it's something more useful for experimentalists. I mean, if you tell experimentalists to measure bipartite entanglement entropies, they will just look at you, and it's not linked to observables, but this quantum Fisher information is basically an integral over chi double prime, which is linked to your structure factor measured in inelastic neutron scattering, convoluted with some tangent hyperbolic, which they call some entanglement filter function. So once you measure this, you can just carry out this integral and calculate something which is claimed to carry some information about the entanglement. So you might also think that some features like this might have some signatures of quantum criticality, right? And there is maybe some enhancement of this. But I mean, this is also just hypothetical, right? Because there was a lot of activity also whether you can look at von Neumann-Renyi entanglement entropies and if there is any clear feature at quantum phase transitions in these entanglement entropies, and the same questions arise in measures like the quantum Fisher information. Okay, so that's basically it. So let me just quickly make the main points again. So, so the first point, which I think is perhaps obvious, but I think it's neat because it comes out of the relatively simple mathematics, is that the topological phase transition away from the exactly solvable point is no longer trivial. And what we've shown is that in the effective low energy theory, all the interactions disappear if we go to the pure Kitaev limit. But if we switch on any other interaction, then we get these interactions. We can then use this to coarse grain the theory and derive some effective long wavelengths field theory, which looks pretty much like a Gross-Neveu-Yukawa field theory. But the Yukawa coupling is of a different form. And this results in a slightly different IR scaling form of the propagator for the bosonic fluctuation field and a different set of critical exponents. Right, but some of the key features remain, like this resulting non-Fermi liquid behavior. And as I discussed, there are potentially signatures. I mean, there will be signatures in inelastic neutron scattering. The question is if we can get the materials to this point, and if the next generation of experiments have enough low energy resolution to really get information out of the particular form of the continua. Okay, so that's it. Oh, I'm slightly over time.
Thank you, Frank. Virtual clock. Let me open the floor for questions. You can unmute yourself, you can raise your hand, or you can write them in chat and I can read them. Just to start the conversation. So we've started to look at RICs, right, as a possible alternative to also look at the continuum and Kitaev candidate materials. We measure hydrogen, lithium, iridium oxide, and we saw what seems to be, of course, without the energy resolution of neutron scattering, inelastic neutron scattering, we see signatures of a continuum. So to me, there are two questions. What about any other type of interactions that you may have in these real materials that might take you away, like off diagonal terms, Heisenberg J's? Would you expect to see this topological phase transition in those systems too?
Yes, I mean the point is the Kitaev quantum spin liquid is stable, right? I mean it's only stable up to, you see here, the J you need is just 0.02 times
right.
But there will always be a regime where the Kitaev quantum spin liquid is stable against any other form of interaction. I mean, of course, you can, if you apply a magnetic field, you immediately open a gap. And I guess there are other couplings that could open a gap. Particular forms of DM probably would open a gap. And but in general, you expect that this topological transition will remain. And I mean, there are other situations where you can have potentially larger perturbations, but different perturbations which have some mutual cancellation in a way, right? That if you simultaneously ramp up certain interactions, But
Yeah,
I
that's
also know that there is a pretty well-developed theory for Rick's experiments of quantum spin liquids. There is a paper by they also looked at inelastic neutron scattering, but also at Rick's. I think Natalia Perkins has done quite a lot of work, and Roderick and Johannes Nolle.
right.
So what they all do is they use the parton mean field, the parton construction in terms of Majorana fermions. Usually, because you don't want to only switch on Ising couplings, they use the original Kitaev version. And you have the additional constraint to deal with through Lagrange multipliers or whatever. And the problem is you have an interacting Hamiltonian, so you can then use mean field and can add fluctuations beyond mean field. And this is what they have basically done and related to Rick's and inelastic scattering. I've recently seen an interesting alternative where they use the interacting Hamiltonian and then instead use the variational wave function, similar to what people use for strongly correlated electron systems, like for variation of Monte Carlo, right? Like a Gutzwiller projected Slater determinant plus Jastrow factor. Then you basically get the ground state, and then by adding some particle hole excitations, you can get the excitations. And the spectra they got looked very similar to what they got from DMRG.
I see.
At least that's what I've seen at the March meeting. And which is quite impressive and useful, because from these variational wave functions, you can actually link it back to various physical observables.
Right.
And understand more of the underlying physics.
Right. I see.
But yeah, so I think the topological phase transition is always there, but you need to be in the quantum spin liquid region. So I think this phase diagram will always look somewhat similar.
Right. Well, in terms of modifying, the magnetic exchange interactions in a different way, one of the things that we want to try is light induced. That's why I bring the Rick's idea. Martin Klassen has a couple of papers that you say if you go with a Fouquet pulse, you can renormalize some of the hopping integrals through the ligands, and then potentially you can vary the intensities, the relative intensity of the exchange parameters. So of course, this is all in theory. We want to try the experiment, but it could be an opportunity to tune, if it works, to tune all these different parameters in the Hamiltonian.
Yes.
Any other questions? Okay, then let me thank you again, Frank. This was really interesting. I think we are over time, so we can stop it here.
Yeah, I hope it was not too much detail.
No, this was really interesting.
I wasn't sure if okay. Good. Okay, thanks a lot. And please let me know when you are visiting. We can.
And if you're in Boston, please let us know, and we can invite you in person.
Yes. Yeah, I've met your students.
Yes. That's right.
Okay, have a good day.
Okay. Bye, Frank. Thank you.